and again the frequency converters or these frequency controlled switches operate. And by constantly switching these, the frequency is maintained at 50 Hertz. Not as good as in Central Europe, but good enough for everything else. It probably varies between, I would think, between perhaps 48 and 52 Hertz or something like that, which is huge, large scale system is terrible. But for this is so they don't have a battery. But they would probably be well off if they had a battery. That probably would be an improvement to the system even. So when you have an autonomous system, you need to have a battery, and I think it also then needs to be a lead acid battery because everything else is so expensive. And so what I've also now done is that ist Ihnen zu kalt?
Ja, aber jetzt nicht mehr.
Is it cold for you?
For me it's not. Okay. Maybe I'll accept.
Ich bin auch ein bisschen dünn angezogen.
Tut mir leid jetzt.
Nein, das ist alles, ich bin gut ausgerüstet, kein Problem. Nein. Okay. Das ist 16 Grad ist, glaube ich, die optimale Temperatur. 16 degrees also. It's very good for energetic, be energetic the whole day. And I'm not, in the moment, not adapted to this, but it's, I think this is the best we can do.
Well, we do have central heating. One thing that I forgot to say about the University of Clausthal.
Ich muss mal kurz stören. Hat einer von Ihnen ein Volvo?
Oh ja.
Möglicherweise Wolfenbüttler Kennzeichen, irgendwas mit 56 hinten? Ja. Könnten Sie den bitte mal wegstellen, woanders hin? Der steht auf dem reservierten Parkplatz für unsere Herren Professoren vom anderen Institut auch noch. Ganz schlecht. Professor Bohn hat sich gerade beschwert.
One thing that I forgot to say about the University of Clausthal. The joke is that it's the only German university with 2 winter terms.
Oh, okay.
Even when it's summer in the rest of Germany.
It's always winter.
It's cold here.
Yes, I heard about some students from Indonesia who have already finished from Clausthal. It's very cold. Yeah. Actually, Clausthal is also a very famous university. Yeah, I heard more about this.
Very special. Isn't one of your didn't you have your prime minister? Didn't he study in German?
President.
Our president.
From
Habibi.
Yeah.
Habibi, okay. Mr. Habibi.
Yeah. No, he is living in Hamburg.
Oh, okay.
Yeah.
Okay.
He's very close to Germany.
Yeah, because there was an interview with him once on German television,
really?
and he spoke excellent German.
Yeah.
I thought, and then they said that he'd studied somewhere in Germany.
He has some patents here in Germany regarding the aeronautics.
He's expert in
aeroplane is
Yeah.
expert about this.
And of course, there are quite a number of Chinese students here. And a couple of years ago, the Prime Minister of the state of Lower Saxony went to China on a state visit, and the universities of Lower Saxony organized a meeting for him with Chinese scientists, and they selected only professors and scientists who had studied in Germany. So he came into this room expecting that he would always have to have an interpreter at his side, and he was just stunned that everybody spoke German to him. Okay. How's your German?
No, I still try to study more.
Very good, very good. I'm not quite sure whether I, but by sort of, explaining and talking about these, I talk about things that are of interest to you. I have printed out, and I noticed that it's in German. I asked Hoppiger, one of my students is now at Hoppiger, and I said, can you send me some information about solar battery systems? And he said yes. I said it was Indonesian visitors, and he said yes, and he sent me still the German. Okay. I thought of using that literature perhaps to explain, from my point of view, what you should be observing when using batteries for renewable energy systems.
Hinten war alles frei. Also.
But is that okay if I just, talk about what this system and then talk about batteries? Okay. How much do you know about batteries?
Actually, it's a new thing for us, so
Okay.
I don't have any background about batteries.
So you know there are two metal and if you touch them, yes, depending on it can be quite dangerous. Yeah. And it can be in fact very dangerous. And probably what you'd be in large autonomous energy systems, one has batteries with a nominal voltage of 500, 600, 700 volts. These are really deadly if you don't handle them with care. But also the smaller systems, the 48 volt telecommunication systems or 24 volts. What you might have in smaller battery systems, they still offer risks if you short circuit them. One risk is you just get a shock. And you go like that and hit yourself. Okay, and you have a blister but if the batteries are big, then the short circuit won't just disappear. It will draw a spark, and it will tend to draw the spark where your hand is, so you can have severe burning. And of course batteries may explode, so batteries offer potential hazards, and so I think ideally, I think you want to advise people what to do and how to do it. I think batteries should be in some sort of containment, and that the ordinary user cannot actually get at them. Not get at them in terms of the electrical parts. It's they're just risks of fire, risks of explosion, risks of whatever. And people who produce batteries and who sell batteries should know all about that, and so they would tell you what to look out for and what to do. There are perhaps there's three things that you ought to know about batteries in terms of selecting the right product. The first thing is so the mechanics. In a battery there are no moving parts, so nothing moves. Okay. When you look at it in detail, you have a conversion of materials, you know, the charged and discharged material, and if you go from charged to discharged, in the lead acid battery that's lead and lead dioxide, and it's powder, it's very porous. You go to lead sulfide, PbSO4, and the transfer from this to that is volume times 2, conductivity times 10 to the minus 12. This is reasonably well conducting, not as well conducting as copper, obviously, but it's a reasonably good metal conducting material. Lead sulfide is a non-conductor. It's a really poor non-conductor. And the other thing is it has a different crystal structure. So we have a conducting, and something else. It forms large crystals. Here the crystal size is sort of 0.5 to 1 micron when the battery is new, and when you don't use this battery well, the large crystal size here is, I don't know, 10 to 25 microns. So when you charge and discharge a battery, you have a porous, well-conducting, structured, small crystals, and you convert it into a structure with large crystals, twice the volume, non-conducting. And in order to do that more than once, to do it once is no problem. To do it, in industrial lead acid batteries, you do it something like 1,200 times. In order to do that, you need to restrict the amount of lead sulfide that you form. You need to restrict the depth of discharge. If this battery has 100 ampere hours, the less you take out, the longer the lifetime. So if you only take out, I don't know, 50 ampere hours, you might have something like 2,500 cycles. If you take out 100 ampere hours, you may have, I don't know, 1,000. If you take out 120 ampere hours, which is possible when you use very, very small currents, it may go down to, I don't know, 50 cycles. So you have to limit the level of discharge. And basically you have a selection, you have a choice. Either you buy a small battery, you discharge it deeply and have to replace it quite frequently, or you buy a bigger battery with a lower average depth of discharge and a longer life. And it all has to do with that. Yeah? So that's the first thing. The second thing is charging. During charging, what you do is you convert water in the electrolyte to hydrogen and oxygen, which is highly explosive. Okay. And apart from being highly explosive, that process is also damaging to the battery. So discharging the battery constantly deep is bad. Always having the battery on charge and charging it, fiercely is also bad. So you have to restrict the use of the battery here, and you have to restrict the battery use of the battery here. Unfortunately, this process is also necessary for really fully charging the battery. So sometimes, perhaps once every 2 weeks, once every 4 weeks, you have to, as they say, bite the bullet and really charge it fully. If you don't do that, the battery lifetime is also shorter.
But how about if the battery is overcharged? Overcharged.
It's overcharged, yes.
Yeah.
What happens?
Okay. Yeah, what happened? Is also the lifetime become
shorter.
Yes.
shortened
Yes.
also.
The lifetime. One way of overcharging is increasing the voltage. It depends on the system what an overcharge voltage is, but if you use a voltage per cell level in excess of, let's say, 2.45 volts per cell continuously, you have this process, and in addition you have corrosion. Lead is transferred into Sie haben doch einen Rechner da, gell? Darf ich mal gucken, ob ich da...
Ich kann das schnell eingeben.
Ich muss mal gucken, ob ich da... Nee, ich habe das nicht da drauf. Ja. Okay.
PP oxide.
Lead is corroded,
Yeah.
and it forms lead sulfide. That process is possible. Lead in the collectors and the lead parts, but the other way around is not possible anymore, and the material bends. You will find that the no, I don't have it with me. I perhaps should have taken that information with me, but I didn't think that I should have planned more. Okay.
What is the meaning of the overcharge? Is it too much current?
It's
Or-
the voltage does the damage. The voltage does the damage. Yeah. And the voltage on a continuous basis does the damage. And it uses up hydrogen, it uses up water, and it just destroys the lead. An overcharged battery, the internal construction of the battery will just disintegrate. It just the metal parts just, you can, where before, the metal parts are soldered together and very strong. Afterwards you just take them, pull them apart, and that's it. And there's no electrical connection anymore, and so overcharge is also that. So in order to prevent this, I won't say all, but a reasonably well designed renewable energy system looks like this. You have here your photovoltaic module, you have here your solar controller, and here you have your battery, and here your load. And this solar controller is set in such a way that the okay, you measure the voltage here. How do I explain this here? Voltage of the this is ground, okay? Voltage, and that is the input to the switch in such a way that the voltage here is not
No.
exceeded. Yeah. And so this is for overcharge control. And the other thing is you have here a switch which is the deep discharge control. If the battery is deeply discharged and it disconnects. And often this is one unit. Steker, for instance, I think Steker is a pretty. They have a very high market share, don't they? Steker?
Yeah, could be, yes. So they also have a branch in Indonesia.
Das ist neben Memmingen. Sie haben mit denen nicht wirklich viel zu tun, oder?
It starts now. Now we develop this and getting maybe their distributor in Indonesia. So they are in Memmingen, huh?
Memmingen,
Yeah.
Steker, for instance, produces a unit which is both a solar controller and
Inside this
in
infrastructure.
one unit. Yeah. And it disconnects the battery when it's overcharged, when the battery gets discharged, and it protects the battery from overcharge. And the better systems have here not just a switch, but DC-DC controller, which usually has this maximum power point tracking. You're aware of that? Where you have the power, voltage over current. This is the PV module, and so here is the maximum power, and the battery has a characteristic which looks like this. Okay. If it's fully charged, or like this is if it's anyway, if you simply connect the systems, photovoltaic module and battery, then they will have a common voltage. So the photovoltaic module will not produce at peak power, and the battery will not receive the correct voltage. So the hard connection of battery and photovoltaics, I don't think it's done anymore. When I was considerably younger, so young like you, that's what people did. Not anymore. That is the standard, and in fact, quite frequently it has maximum power point tracking in order to really optimize that, because cost difference is not really that big. And all that in order to make sure that the battery is protected against deep discharge, and the battery is protected against overcharge. This deep discharge control so cheap systems, they just use the voltage, and better systems calculate state of charge of the battery and use the state of charge to switch off the system. The reason is that if the load draws high powers, high currents for a short period of time, the voltage will go down, the system will disconnect, but there's no need to disconnect it because it's just a few seconds. So the system would disconnect too early. But also if the system, if there's a very small load, but for a long period of time, the voltage goes down very, very slowly for a very, very long period of time. The voltage limit is not reached, but the battery has drawn 120, 130, 150 ampere hours. Like you have a tiny little lamp on 100 ampere hours with, I don't know, 2 watts. The battery will go on for hundreds of hours. The voltage could be quite high, but you will destroy the battery. So state of charge would be the better way to do it. There are probably, again, you know, if your price sort of goes, if your price increases like that, you probably have sort of sophisticated state of charge calculation. State of charge you can only calculate, you cannot measure it. And a good programmer will have a poor state of charge control, and a good programmer will have a much better one. And yeah, so I would presume that the more high-tech a company is, the more technology base they have, you know, they're more sophisticated. They will have a look at that. If you take the cheapest of the cheap solar state of charge controller, they won't have the money to, you know, to employ people like you to work out the algorithm. It's by no means simple. If you have students, they write bachelor degrees and things like that, and bachelor thesis.
Right now, me no, but my colleague have.
Okay.
Mr. Purnama.
Well, if you have a bright student, ask him to do it as a state of charge controller.
Okay.
Yeah, this is also the issue.
Yeah.
It's
Very difficult.
It's not straightforward.
I have asked with the Hopical people, and they don't have this
Yeah.
until now.
The reason why it's difficult is that you calculate it on measured data, and whatever you measure is not really reality.
Yes.
And over many, many days and weeks, what you measure and calculate and reality, you know, get further and further apart. So you always have to have a kind of a reset point. You have to say, now the battery is full, I'm 100% state of charge. Or I've now reached a point where the state of charge must be higher than 90%. It cannot be any other way. Fraunhofer in Freiburg have an extremely good state of charge control system, but they only sell it on license. Okay, but state of charge control for switching off would be, you know, much better. Okay, and then there is something else that you need to know, which is about the design of batteries. Okay, all batteries look like this. There's a positive electrode, there's a negative electrode. Okay, and here current goes in, and here the current goes out. The electrons, the current goes the other way around. But the flow of electrons is from the negative to the positive.
Yes.
And what happens in batteries is that there's more current here than here at the bottom. Obviously, because this has a much higher resistance than this. You know, that route is electrically shorter than this here, so there'll be, you know, more current here. Now that more current means that more of the acid is converted to PbSO4,